Thank you, Ludovico, for the introduction. So we'll be talking about error analysis of this task called anti-distinguishability in both classical and quantum setting. We'll be more precisely, we'll be talking about the optimal error exponent in the asymptotic regime. We'll be getting into the details slowly. So this anti-distinguishability task can be thought of as like a dual of the discrimination task. We know that the usual discrimination task is that we have a quantum system prepared from a randomly chosen quantum state, which are a priori known, and then you perform some measurement. Based on the measurement outcome, you guess what is the true state of the system. So in anti-distinguishability, we flip the question. Based on the output of the measurement, you select a state that is not the true state of the system. So, all right. So this anti-distinguishability can be thought of like this game. We have a set of known quantum states, say R states, and a state is given to you by a referee. Suppose the player of the game, and a state is given by the referee. You don't know what the state is, the referee knows, and you can perform measurements on the state. And based on the measurement outcome, your task is to determine a state not given to you. So for instance, here's an instance. Suppose the referee has state ρ1 and gives to the player and asks the question, which state did I not give you? So if the player answers that you did not give me ρ1, he loses because clearly ρ1 was given to him. Another instance is that same question is being asked by the referee. Suppose he has ρ1 as the state and gives to the player. Player can do measurements and answer which state was not given to him. Then in that case, if he answers that you did not give me ρ2, then player wins that round of the game. So
it uses a plus of one.
Yeah. I mean, it's like the more the number of states, easier it is for you to be right?
It's like there's a bomb in a bomb in like a series of bombs. There's only one bomb, and you have to pick the box where the bomb is not.
Yes. So more precisely, we have a system suppose prepared. So for the purpose of the talk, we'll assume uniform prior on the given states. So suppose a state is chosen uniformly randomly from ρ1 up to ρr, and a system is prepared. You can perform a measurement using a POVM, which will be a set of positive semi-definite operators, R of them. And outcome I of the measurement says that ρi is not the true state of the system. So if ρi was the true state of the system, the probability of getting outcome I for corresponding to that POVM is given by the Born rule. It's trace of ρi times mi. And if the system is in state ρi and the output is I, you have committed an error. The POVM has committed an error for the anti-distinguishability task. So the average error probability corresponding to that POVM is this quantity. It is the sum of 1 over R times the sum of the probabilities for each of the outcomes. So this is the error. Anti-distinguishability error will be concerned with. So, okay, the anti-distinguishability task, it's fine, like it's interesting mathematically, but why is it important to look into it? Well, it turns out that anti-distinguishability has several applications. To begin with, it has been used to answer some fundamental questions about quantum states. There is this theorem known as PBR theorem, named after the authors. In this theorem, the authors ask this question. They basically study reality of quantum states. They ask this question: is a quantum state merely information about some larger physical system, or is it something that represents a physical system? So there has been a history of debates about the reality of quantum states. from the times of Einstein and Bohr. So in this particular paper, the authors eliminate an epistemic model of quantum states. An epistemic model says that a quantum state is merely it merely represents information about a physical system, but they said that this assumption leads to some contradictions. There they use anti-distinguishability task, and they prove that quantum states are actually real. They represent physical systems. So, and anti-distinguishability also has applications in quantum cryptography. Turns out that one of the papers on quantum cryptography claims that this can be used to realize quantum digital signatures without the requirement of long quantum memory. Yeah, and there are several other applications that are there. You can see them. And recently, I also came to know about this something called doubling coefficient. It's from classical computer science information theory. It also has a quantum version of it, and it turns out that doubling coefficient has something to do with error probability of the anti-distinguishability task. I did not include the details of that in this, but that is something I recently came to know and would like to explore more on that. Anyway, so given that there are some interesting applications, yeah.
So just a quick question, the unambiguous quantum state elimination, is it the same game, but you allow yourself to say don't know with some probability? Is that the idea?
I think don't know is like an inconclusive thing. Like when you say
It's like if
here you're like conclusively saying that, oh, this is not this is just like the discrimination task. It's just that you're answering a different question. Yeah. You do say, based on the measurement outcome, you do say that, oh, this is not the true state of the system.
Okay.
Yeah. All right. So yeah. So apart from the applications, this problem itself is mathematically interesting. So it was fun to work on it. So let me get to the main ideas. So let's talk about optimal error probability. So optimal error probability is the usual definition. The error for the POVM is that sum 1 over R summation over trace of rho I mi. So you are taking infimum over all POVMs. So that gives you the optimal error probability, like the least error you're going to commit for the given anti-distinguishability task for the quantum states. And if the optimal error is 0, then the states are said to be perfectly anti-distinguishable, meaning without any error, you will be able to say that what is not a true state, you will be able to give a state which is not the true state of the system. But in general, states are not perfectly anti-distinguishable. For example, a simple example is R equal to 2 case, where anti-distinguishability is the same as distinguishability. When you say that this is not the true state of the system, the other one is the true state. So you're answering the same question in R equal to 2. Things start to get interesting when R is greater than 2. That's when the distinction comes. So yeah, if you consider two states that are not orthogonal to each other, then we know that they cannot be perfectly distinguished from each other, which also means that they cannot be perfectly anti-distinguished from each other, meaning the optimal error is going to be strictly greater than 0.
So you're saying if R is greater than 2, there could be a collection of rho 1 up to rho R where the anti-distinguishable and distinguishable problems are not same.
Yeah, of course. Yeah, like just to give you an intuition, if there are 10 states, like if suppose you do not have any strategy, if a referee is asking what is this, what state did I not give you, you can select any state. Say you say you did not give me rho 1. Suppose that is your strategy. You are more likely to be correct than answering the question that which state did I give you. So you see, so you have 9 ways of being correct in the anti-distinguishability task, but only one way of being correct for the discrimination task.
Yes, but that doesn't still mean perfectly, right? Like there is still an error in my answer.
Yeah.
So you should say So like,
The error is zero.
yeah, you're asking whether the error can be zero for distinguishability, but not for the
Yeah,
You can have
yeah,
row 1 up to row 5 being equal, and then row 6 up to row 10 being orthogonal and also equal. And you'll never succeed in distinguishability that collaborate when it comes to. But I give you row 1 and row 6 up to row 10, so you're going to go down, so it's vice versa.
Yeah, I mean, another example would be you consider, say, three states, two of which are orthogonal to each other. I think that's what we are trying to say. But not all of them are mutually orthogonal to each other. Then we know that that is not perfectly distinguishable because necessary and sufficient condition is that they should be pairwise mutually orthogonal. But a sufficient condition for anti-distinguishability is that two of them, some pair is orthogonal to each other. That is a sufficient condition, but that's not a necessary condition. So yeah, that's another problem. We do not know an easy, necessary, and sufficient condition for anti-distinguishability. There are some conditions based on some SDPs, and the conditions I do not find very easy to state. So yes, so yeah, those are some distinctions. So okay, getting back to this optimal error probabilities. This is very nice. Now let us go into the asymptotic error exponent. Now the title of my talk is on the optimal error exponent for the anti-distinguishability quantum and classical. So that optimal word, when I used that in the previous talk, it was creating some confusion. So I'm instead going to use this asymptotic error exponent. So what we mean by that? So instead of one states, we have n copies of states, and so we can perform measurements on n copies at once, and it is shown that we can actually very easily show that the optimal error in that case, as you increase the number of copies, that decays to zero exponentially, and it's the exponential in the n tending to infinity case we are interested in. So this is how we define asymptotic error exponent. So it is limit of -1 by n natural log of the error. So that's going to be our definition for the asymptotic error exponent. And it is this quantity we are after, both in the quantum case and in the classical case. Let's talk about the quantum case first. All right. So one of the things we do is we first begin with giving an upper bound on the optimal error probability. So we know that so it is well known that if you have two states, then the optimal error probability of distinguishing between them with uniform prior is given by this quantity right here, and this optimal error probability is achieved by the so-called Hemant measurement for the R equal to 2 case. And so it means that for each pair, if we restrict our POVMs, if we only consider the class of POVMs where only two of the POVM operators are there and rest all of them are zero, then you could restrict the infimum to a smaller set and you get an upper bound on the optimal error probability for the anti-distinguishability task in terms of the pairwise errors. So there is some normalizing factor that comes in, and so this happens. So with this simple observation, we get an upper bound on the optimal error probability for the anti-distinguishability task. And this optimal, this upper bound can be achieved by this Hemant measurement. The only difference is that the order is flipped. In the original Hemant measurement, there was the original Hemant measurement has this rho I flipped with rho j. That's because in the discrimination task we are trying to maximize the same expression, but in the anti-distinguishability task we are trying to minimize the expression, and it turns out that if you flip the order, then this POVM achieves the optimal error in the anti-distinguishability task. Like it achieves that a minimum error probability.
But are these things symmetric? I mean, the trace distance, no, you can flip sigma and rho. Yes, they're the same.
Yeah, but this MI will, you know, but this is a projector onto that.
Oh, okay. Yeah.
But still, like, I don't see why they would.
I mean, like if you flip this rho j and rho I in the second to last equation, then the operator changes.
Or isn't it just the other one? Then?
Yeah, it's just the other one. Yeah,
So you do the Ross measurement, then you give the option down.
yeah, exactly.
You just say like when you have a check, then
Or you
Gotta read
could
it.
say, what did that make?
That's flipping.
Yeah. So this flipping was important. I cannot exactly recall how exactly it was playing out. But yeah, this flipping is
Because you're just guessing the other one.
yeah, I was saying like, do I?
Oh, yeah,
is-
yeah.
Is it
Oh, yeah,
look
yeah.
like road?
That's
J,
what-
then it better not
yeah,
say
yeah.
road J.
even though the problem is same, but you're trying to answer the question in a different way. So this one works. Perfect.
So is the distribution uniform over the states?
Yeah, that's what we are assuming. But
Factor probably is 2 over R.
yeah, that's exactly right. In fact, we could work with any prior instead of working with uniform prior. The asymptotic resultants are to be same in all of them. So the asymptotic error exponent, for example, is independent of the choice of prior. So for the purpose of the talk, I consider uniform prior. It's easy to state and like.
So how restrictive is it to take in the theorem satisfying that they have absolute identity for each pair IJ?
This one. So what we are doing is we want to get an upper bound on the optimal error in terms of pairs.
Yeah.
So we first choose a pair, then only consider those
Okay.
class of POVs
Okay.
for which that.
It's like you play with the person and
Yeah, it's like
you take the best pair. That's the main one.
yeah. It turns out that it is bounded by about from the pairwise minimum error probability with some constant.
There was a paper recently about the diagram.
Yeah, it is. That's a good question. That is related. Just like the pretty good measurement gives you near optimal error probability. The pretty bad measurement gives you near optimal error. Well, that's not something they state explicitly. That's something to verify. But they do say that it does pretty good. The pretty bad measurement does pretty good for the anti-discrimination task. So that's something we should verify.
So given row 1 up to row R, is it easy to determine which I and J minimum are?
I think
I guess, yeah,
So-
I guess it's finite computation. Yeah, I don't know.
I mean,
Yeah.
there's BPs.
Yeah,
so
yeah.
it's fine, but that's
Yeah.
fine.
yeah. All right.
Yeah.
Very nice. Okay, so this so we have an upper bound. Now that we have an upper bound on the optimal error probability, that is going to give us an achievability bound on the asymptotic error exponent. Let me get to what I'm trying to say. So now that we have an upper bound, we can consider these asymptotic case. So suppose we have n copies, we have an upper bound on the optimal error for that n copies ensemble from the previous slide. So if you just simply do the mathematics, you get -1 over n times the log of the left hand side is greater than or equal to the quantity on the right hand side. Now, as n tends to infinity, the first term vanishes. So the only interesting term is the second one. But that term is actually known. It is given by the quantum churn of divergence. If you take n tending to infinity, the limit exists, not just a limit. The limit exists in the for the second term, and it is given by the well-known quantum churn of divergence between the two states. So that's something that was proved in the works of Nussbaum, one of the co-authors of this paper, and Nussbaum and Shkoa was a paper showing one side of this churn of divergence bound, and there was this paper by Hardenard and co-authors. There they proved the other side. Anyway, so this thing is known. So that's nice. With that thing, we get Okay, this is asymptotic error exponent for discriminating the two states. So using that last slide, that inequality, we get a lower bound on the optimal error exponent, which turns out to be the pairwise maximum Chernoff divergence of the states. And it turns out that the above inequality can be strict, and this is an example. In fact, it's a classical example. The states are commuting, which shows that that inequality can be strict. Actually, when we found out that, so from the beginning we were after the exact error exponent in the asymptotic case, but when we found out that there can be strict inequality, we were like taken aback a little bit, because we were expecting that there will be equality there. Why? Well, just a hunch. It was like for the state discrimination task, it turns out that the error exponent, the asymptotic error exponent, is given by pairwise minimum Chernoff divergence. It would have been very cool if this was given by pairwise maximum Chernoff divergence, but that is clearly not the case, which makes these things even more interesting. Like, then what is it? Anyway, so this is not the exact expression. This is just an achievable bound on the asymptotic error exponent. All right. Now, so we have found a one-side inequality for the asymptotic error exponent. Now, what I'm going to discuss is going to give you the optimality bound on the error exponent. So for that, just quickly recall that primal SDPs and dual SDPs. If your primal SDP is of that form, its dual SDP is of this form. Then where A, B are Hermitian operators, and capital Phi is the Hermicity preserving superoperator. Many of you are already expert on SDPs. I just wanted to recall this just to jog your memory. Okay. Now we get a lower bound on the optimal error probability. How do we do that? We can represent the optimal error probability in this SDP form. So if you look at the first SDP, that's nothing but the definition of the optimal error probability. You want to take infimum of that average error subject to the P variance. And if you calculate the dual of this SDP, turns out to be the second SDP that is there, and it turns out that strong duality holds for this dual SDP, and the answer you get in the second one is the same as the first one. That's why the equality, and this was proved in this 2014 paper. So the second SDP that you have, if you look at the constraint, it's a supremum mode trace of y, where y is a Hermitian operator, and y has to be less than or equal to 1 over I times rho I for all I. I mean, that's the original problem, like what is that quantity for the asymptotic case. But what we did was we considered this constraint. We imposed extra constraint that not only y should be bounded above by that quantity for all rho I, it should also be bounded below from the negative of that. Well, why did we do that? Because there is an interesting quantity related to this thing. Let's denote that by one normalizing factor times kappa of rho 1 up to rho r. And it turns out this quantity is super multiplicative, which is very nice, because using this property, we get this upper bound or optimality bound on the asymptotic error exponent for the antidistinguishability task. Right, and again, this kappa is an interesting quantity because it's related to something called extended max relative entropy. So the max relative entropy is defined for any Hermitian operator X and any positive semi-definite operator sigma, both of them non-zero. That's the definition. And if you look at the definition of D max, it resembles somewhat like what we have for the kappa. Right, so we have upper bound and lower bound both on X, and that was the resemblance. And using that thing with some basic mathematics, you can show that this quantity left hand side is bounded above by this regularized or optimized Dmax, extended Dmax quantity. And the quantity in the left hand side was already an upper bound on the optimal, on the asymptotic error exponent. So we get another upper bound on the.
So could you go back a couple slides? Yeah, one more. So in this final expression, is there actually a case where you need to have negative eigenvalue for this line? Because it seems like you could just make the eigenvalue to be zero, like why would it go negative? Like you put this lower bound to be negative.
Yeah, when I was working on it, I also had similar thought, like we don't really need to have y with negative eigenvalue, but it turns out that this quantity and that quantity are strictly not equal in general. Like you do have the need of negative eigenvalues of y. I mean, sure, the trace of y can be like it has to be positive, but there's something going on. Like you need negative eigenvalues.
And it can help you to satisfy the upper inequality. So like y upper bound by something, negative eigenvalues can help.
Like, I guess there must be an example where it is, because it seems like you could just bump it up to zero, but sometimes.
Yeah, yeah, that's true.
All right.
Yeah, maybe I should include that example for the next one. Yeah, I mean that would be interesting too.
Sorry, what was the definition of kappa?
Oh, it's this with that normalization factor. So you take r with y, so just do that and you get kappa. That's it. Okay, so this is what we have got so far for the asymptotic error exponent. So we got an upper bound in terms of kappa, which is also bounded above by this extended Dmax quantity. And that's all we know about the asymptotic error exponent for the quantum case. Yeah, it is still a wide open question to answer the this question for exact error exponent. We don't really know. So this is just a summary of what we did for the quantum case. Let's get to the classical antidistinguishability. Well, in the paper, we have the classical theory first and then the quantum theory first. But when we started working on it, we started with the quantum and then went to the classical because of that example where the inequality was taken. So I chose to present it in this way. So what is classical antidistinguishability? Exactly like what we had for the quantum case, only for commuting states. So an example of classical antidistinguishability is this. Suppose you have three biased dies of different colors, and suppose one of the dice is selected at random and is kept by your friend, and you are asked the question, which die does he not hold, right? And what you are allowed to do is you can ask your friend to roll the die and he can give you the output of the roll. You can ask him as many times as you want, and based on the measurement outcome or based on the what you observe on the die, you have to guess what is the color of the die. Of course, you know based on each color, a priori is known that what is the distribution of the numbers on each of the die. So that is the task, and based on the outcome of the measurement, you have to guess a die, the color of a die not given to you. All right. So this is just describing that thing in words, whatever I just said. I'll just move to the next. So formally what is happening is, suppose, so classically we want to anti-distinguish between probability densities. And suppose you have an ensemble of classical probability densities on a measurable set, and a system is known to produce I don't know if I have the right way of explaining what is going on, because it's not, I'm not familiar with nomenclatures here, but I'll try. So suppose there is a black box. So it is known that the black box can give you it can sample data from the sample space, and it is known that the black box has this so whatever data you sample, it follows one distribution, which is randomly chosen from the given ensemble. And based on the outcome, the sampling data you receive, you have to determine, you have to guess a density that the system did not, the black box did not produce. So if going back to that die game, if your friend rolled a die and he got an outcome, and you have to answer which die, what is the color of the die, what is the color of a die that was not given to your friend, the natural selection would be to choose that color which is least likely to produce that color. So that leads us to this this probability probability of anti-distinguishing after observing n data. So the data observed are IID data, mutually independent. So the tensor of n of pk represents the probability distribution of the data. So suppose omega is the observed sample after n observations, and so which die would you, which probability density is the optimal answer? It would be that k for which this quantity is minimum. The probability of obtaining that omega among all of them is minimum. For whichever k is that, you just say that, oh, okay, that was a probability density not produced by the black box or the system, right? So this leads us to this minimum likelihood principle, which gives you the optimal error probability of anti-distinguishing the probability densities, where what you are doing is for the n observations, you're just point-wise, you're taking minimum of the probabilities, and you're just integrating, and 1 over r is the factor corresponding to the uniform prior. As n tends to infinity, the optimal error probability decays to 0 exponentially. It can be shown, and it turns out, and again, the definition of the asymptotic error exponent in the classical case is the same. This is what we are after.
The constant that is positive, you know, like which constant is it, or you know the just exists?
Oh, I mean, so in this work, we also show that this optimal error exponent decays to 0 exponentially. So for every n, for n large, your error probability is going to be something like that.
Yeah.
So,
No, but I mean, do you know like the specific constant given the description of the game, or is it just that you know that it exists a constant?
But I guess that's the purpose of the thing, is to find this exponent, it's constant.
yeah.
But like classically, I guess it must be easier than quantity, right? So you have sort of a closed formula for it, or that's what I wonder.
I don't know for the Zn, but we certainly do solve the problem for n tending to infinity, the asymptotic error exponent. And this problem, of course, it is easier than the quantum case because we were able to solve it, but we were not able to solve the quantum case, I guess. Yeah. The last line is the things we are.
This is constant.
Yeah, exactly.
This is
Yeah, I mean for large n, of course, yeah. So that thing will be somewhat equal to zeta and replace with this quantity. And yes.
In the middle, well, you see that it seems that depends on him, because we're in exchange, we're in exchange numbers,
Yeah. So n is like the number of observations you make. So for large n, this quantity is like
I mean,
exponential.
I think you say like you could put an equality there because you make psi depend on c depend on n minus 1. If you put the
Okay. Yeah. I mean, yeah.
yeah.
So the middle line is the definition of n.
Yeah.
Maybe I can put any equality there, and then we are after what the zeta and for n.
it's a constant.
Cn.
Six,
Yeah.
is it a, but it is a constant, you're saying, right? It's
It's
not
a-
like, it's not like the case like exponential or, psi n can be 1 over square root n, something like that, so the k is actually e to the minus square root n, it's actually.
Yeah, I
It
mean,
is-
that,
it
that's
is a constant.
one scenario.
No, but it has to be exponentially, right?
So that's what I'm wondering, does it have to be like, does it have to be the form e to the minus quarter n, not like big beta?
And then this kind of IID
Yeah.
things, they're always
Yeah, that's-
exponentially then.
That's what I assume.
Yeah, yeah.
Okay, anyway.
So at the end, it will be clear that that is indeed
Yeah,
like that.
Yeah,
exponent.
it doesn't depend on n, psi.
So
the limit,
for
sorry.
finite and it
For
has to
finite
depend,
n, sure,
but for in the limit, yeah, it's a quantity, like it doesn't depend.
Yes,
Is it psi or xi?
I say psi. but I
I
don't know. I can
think
very well be wrong.
psi,
Does anyone agree?
definitely not Z. Yeah. All right, so before giving you the main result, like what that quantity is, let me recall this Hellinger transform or Hellinger integral of probability densities. It is defined like this. So the given probability densities where mu is a dominating, it's a measure with respect to which all those are densities. So you take so Hellinger transform is a function of probability vectors. Give me R probability vector, like R tuple, non-negative numbers adding to 1. Then you associate with that probability vector with that integral. It's a real valued function. That's a well-known quantity. Have been used decades before, and yeah, it has been used several times. And this is a quantity we define, multivariate Chernoff divergence of probability densities to be minus logarithm of infimum of that Hellinger transform. And interesting thing about that definition is for R equal to 2, that expression is precisely the well-known Chernoff divergence between the two densities. Which you can see from the Hellinger transform, like if you have R equal to 2 and you take the definition like this, that's the definition of Chernoff divergence between the densities. And another interesting thing is that Chernoff divergence is known to be the optimal error exponent for distinguishing two probability densities, the classical version of the quantum one. So if you have two probability densities, the asymptotic error exponent for distinguishing them is given by this Chernoff divergence. Again, for the anti-distinguishability task, the hope was that the optimal or the asymptotic error exponent would be pairwise maximum Chernoff divergence, but that doesn't seem to be the case. And what we get is this. The asymptotic error exponent for the classical case is given by this multivariate Chernoff divergence. And this quantity that we define has this operational meaning for the classical anti-distinguishability task. And as in the example we saw that the optimal error exponent can be strictly greater than pairwise maximum Chernoff divergences. So this quantity can be strictly greater than pairwise maximum Chernoff divergence, which can also be seen by restricting to specific type of probability vectors. You get that, like restricting to Si, Sj, adding to 1, and all of them, the rest of them equal to 0. So yeah, this is the classical result. So this is, I guess, the summary of what we have. I do not want to get into the technical proof of this. One side is easier to solve, but the other side requires some law of large numbers, and then there is this exponential family trick that Professor Nussbaum used in his prior paper, and that's a technique being employed here and turns out to work for the classical case. So yeah, I guess I'll just end with the grand open question. What is the exact asymptotic error exponent for the quantum anti-distinguishability case? That's the open question, and thank you so much. If you have any questions, you can just